Newton's grasp of gravity was sufficient to enable us to travel from the Earth to the Moon. Ever find yourself disoriented in the relentless march of time, questioning if our comprehension of it is merely the surface of a deeper mystery? His discovery is not just a hypothesis. It's a key that could unlock the secrets of the universe, unveiling a cosmos more complex and awe-inspiring than we ever imagined. How does Brian Cox's novel theory challenge our conventional understanding of time? And what could it mean for how we perceive reality? Join us on a fascinating journey through the fabric of time as we explore Brian Cox's recently revealed, groundbreaking hypothesis on the nature of time in the vast cosmos surrounding us. Riddles are waiting to be solved, many of which revolve around strange aspects of time and gravity, both integral components of our existence. Picture a world where time behaves oddly, can either slow down or accelerate. Moreover, the force that keeps us grounded may not be what we think. This is the realm of Albert Einstein's theories of relativity, where our perception of time and gravity takes an unexpected turn. Albert Einstein, a name familiar to all, presented us with a fresh perspective on the universe through his theories of relativity. His work formed the foundation for understanding how time behaves under various circumstances, especially when moving at incredibly high speeds. It all began in the early 20th century when Einstein introduced two revolutionary ideas: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our conception of time and space. Simply put, it asserts that the laws of physics remain consistent for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, such as the well-known idea that time can stretch or slow down under certain circumstances. One captivating thought experiment often used to explain time dilation is the light clock. Imagine being inside a spacecraft moving at an extremely fast speed, near the speed of light. Inside the spacecraft, there's a light beam bouncing between two mirrors, perpendicular to the direction of travel. According to the laws of physics, the speed of light remains constant for all observers, so the light beam must appear to follow a longer diagonal path for the external observer. The time it takes for the light beam to traverse this path should be identical for both the observer inside the spacecraft and the one outside. However, since the path is longer for the outside observer, it seems to take more time for the light to complete its journey. This perceived time difference between the two observers is what Einstein referred to as time dilation. Time moves slower for the observer in motion relative to the stationary one. In this case, time behaves differently, depending on your velocity. Understanding how objects change when they move quickly, also known as relativistic effects, is not merely a theoretical idea. Scientists use large machines like particle accelerators, such as the Large Hadron Collider, to propel particles to near light speeds. When objects move at such high speeds, we must consider time in a special way to make precise predictions and measurements. Albert Einstein introduced the special theory of relativity in 1905, and it revolutionized our understanding of the universe, particularly concerning time and motion. This theory challenges what we might intuitively believe. It states that the principles of physics are the same for everyone, even if they are not at rest. This differs from our everyday experience, where we might assume that if something is already in motion and we add more speed, it simply gets faster. However, Einstein's theory says there's a maximum velocity that nothing can exceed, the speed of light. In this framework, events that seem simultaneous for us might not appear the same to someone moving close to the speed of light. Another concept that arises from this special way of thinking is length contraction. This means that an object appears shorter in the direction it is traveling when viewed from a stationary position. Additionally, there's the famous equation E=mc², which shows that energy and mass are interchangeable. This is crucial for understanding. how tiny particles behave when moving at high speeds, and also for explaining processes like nuclear fission. In the real world, special relativity isn't just an abstract idea. It's something we rely on in everyday technologies, such as GPS. When GPS satellites send signals to your device, they are in motion, and due to this movement, time behaves slightly differently for them. If we didn't account for time dilation in our GPS calculations, your location data would be significantly inaccurate. Thus, special relativity teaches us that time is not uniform across all places and circumstances. It depends on how things are moving. This notion challenges our typical understanding of time and space. It's as if our conventional view of the universe is a bit flawed. According to the special theory of relativity, time isn't constant. It is influenced by motion. Some fundamental ideas, such as the constancy of the speed of light and the relationship between energy and mass, have been confirmed by numerous experiments. However, there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeper into the connection between gravity and the structure of the universe. It reshapes the traditional notion of gravity as merely a force that attracts objects. Instead, it proposes that space and time are warped or curved. It's like saying gravity isn't an invisible force. It's just how things naturally move in the universe. According to Brian's interpretation, general relativity requires thinking about the universe as a four-dimensional entity, combining three spatial dimensions and one temporal dimension. Within this model, large objects like stars, planets, and even us influence the curvature of space and time around them. This curvature is what we perceive as gravity. Imagine space-time as a vast, elastic sheet. When something massive, like Earth, is placed on it, it causes a depression in the sheet. If you place something smaller, like a ball, near Earth, it will roll toward this depression. This is similar to how objects behave due to gravity, not because of some invisible force, but because of the bending of space-time. General relativity offers a robust explanation for the movement of objects in our solar system, such as the orbits of planets around the Sun. It can precisely predict the paths these planets follow, including how Earth traces an elliptical orbit around the Sun. According to Brian, this contrasts with the old idea of gravity simply pulling objects together, which struggles to explain how planets behave. The new theory is that space and time are curved, much like a flexible fabric, which better aligns with what we observe. A landmark event that demonstrated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed close to the sun. According to the theory, the sun's mass would cause the starlight to curve slightly. During the eclipse, the observations confirmed Einstein's predictions, proving the theory's validity. Just as motion can alter our perception of time according to special relativity, gravity also affects time. In regions where gravity is especially intense, time flows more slowly compared to areas with weaker gravity. So, if you were standing near a massive object, like a black hole, your clock would tick more slowly than one placed farther away from this enormous mass. General relativity introduces the idea of black holes, which are regions where gravity is so powerful that not even light can escape. The boundary surrounding a black hole is called the event horizon, and it marks a point of no return. Once an object crosses this boundary, it is drawn into the black hole without any possibility of escape. Einstein's theory of general relativity has profound implications for the structure of the universe. Initially, he added a term called the cosmological constant to his equations because he believed the universe was static. However, upon discovering that the universe is expanding, he referred to this as a great mistake. The idea of an expanding universe based on general relativity is central to the Big Bang theory, which describes the origin of the universe. Another key concept of general relativity is gravitational waves. These are ripples in the fabric of space and time caused by extremely massive objects moving rapidly, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly observed waves of gravitation, providing further proof for Einstein's theory. Over time, scientists have conducted numerous tests to validate general relativity, and each time, the theory has proven to be accurate. Whether by observing planetary motion, the bending of light, or the detection of gravitational waves, general relativity remains a robust and reliable framework. While claiming that gravity is a myth may sound startling, especially since we experience it every day. In the field of physics, it's normal to challenge and reconsider established theories. Scientists like Brian regularly question prevailing wisdom, and in the field of gravity, some propose alternative views. One theory that challenges conventional gravity is modified Newtonian dynamics, MIND, which suggests that gravity behaves differently at low speeds, particularly in galaxies, without needing to invoke dark matter. Instead of positing invisible matter, MIND suggests that gravity strengthens at slow speeds. Also involved in the discussion of gravity are the enigmatic concepts of dark matter and dark energy, which were introduced to explain a few cosmic phenomena. Critics argue that these ideas may be unnecessary and that alternative explanations can account for what we observe. Some scientists who oppose Einstein's theory of gravity explore new possibilities, such as theories involving unknown particles or forces that could change or improve our knowledge of gravity. It's important to recognize that in science, new ideas are not dismissed out of hand. Rather, they undergo rigorous testing to determine whether they hold up. For instance, Einstein's concept of time is part of a four-dimensional continuum where time travel may be limited by the speed of light. This has been creatively explored alongside concepts like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that time travel into the past is unlikely from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can explain phenomena like gravity in a way that aligns with our current understanding. While many ideas have been considered, none have convincingly replaced the well-established principles of gravity. Questioning and rethinking established theories is an essential part of advancing scientific knowledge, fostering research, and a deeper understanding of the universe. In the field of gravity theories, general relativity remains the most significant and successful one. Despite competing ideas and challenges, it consistently performs well in experiments and explains various phenomena, such as planetary motion and the bending of light around massive objects. General relativity endures because it is simple and accommodates a wide array of phenomena. As previously discussed, Einstein's special theory of relativity suggests that time can behave differently depending on your speed. Now, let's explore how this idea affects real-life scenarios, particularly in space exploration. Space exploration is exciting but challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest possible speed. This makes traveling between stars a major challenge, even with advanced technology, due to the long travel times required to reach even the closest stars. To understand what happens to time when traveling in space, consider the famous twin paradox. Picture this. One twin remains on Earth while the other twin embarks on a fast journey to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for the twin on Earth. In essence, they have traveled into the future. Time is critical for space travelers because the longer the trip, the more time slows down. If astronauts were to visit nearby stars where time slows down considerably, they would age more slowly than people on Earth. While this may seem like science fiction, it's a real effect predicted by relativity. Imagine humans sending a crew to a star system far away. Due to the vast distance, the journey could span many years, even if they travel quickly. The astronauts, the spacecraft's passengers, would experience time more slowly because of the time dilation effect. However, from Earth's perspective, significantly more time would pass. Time dilation also affects not just living beings, but technology. Computers and communication devices on spacecraft must account for time dilation for accurate operation. Space travel at high speeds brings physical challenges, such as isolation, exposure to cosmic radiation, and the psychological toll of being far from Earth for an extended period. In our everyday lives, we can observe the effects of time dilation in the GPS, or Global Positioning System, which depends on the precise timing of signals from satellites that are moving. Because these satellites experience time dilation, it's vital to factor in these effects for accurate GPS readings. Neglecting this would lead to substantial errors in navigation. Now, let's look at why time only flows in one direction. Time governs our lives, moving from the past to the present and into the future. This one-way passage of time is fundamental to our reality. But why does time have this one-way nature? To understand this, we turn to the concept of entropy, a measure of disorder or randomness in a system. Entropy, which is tied to the arrow of time, tends to increase as time passes, driving time to move in one direction. The second law of thermodynamics expresses this relationship, stating that in any closed system, total entropy will either increase or remain constant. In simple terms, entropy naturally tends to rise and never decreases on its own. Watching how things move toward greater disorder around us helps us observe the one-way flow of time. Picture a deck of cards neatly arranged. If we shuffle them, they become disordered. This change from order to chaos illustrates the unidirectional nature of time as seen in everyday occurrences like melting ice or stirring a cup of coffee.